In this video, we are going to go over coenzymes and biochemical oxidation reduction reactions. So coenzymes are organic compounds derived from vitamins and they are required by certain enzymes to carry out their catalytic function. The coenzymes in reactions are the oxidizing and reducing agents for the reactions. Coenzymes are chemically changed during the reaction, unlike enzymes that are not changed during the reaction. The coenzymes shuttle electrons between molecules in a biological shell. A molecule in one part of the cell undergoes oxidation by transferring electrons to a coenzyme, thus reducing the coenzyme, and then the reduced coenzyme then carries those electrons to a molecule in another part of the cell that undergoes reduction, therefore oxidizing the coenzyme back to its original form. So the coenzyme is chemically changed during reaction, but it returns to its original state by the end of the reaction. An example of an enzyme are oxidoreductases. Those are the class of enzymes that catalyze oxidation reduction reactions, and they require a coenzyme. So you can see that we have a primary alcohol over here, and the coenzyme used in this reaction is NAD plus, and it goes to NADH plus H plus to do the reaction to get to a ketone, or we have a secondary alcohol to a ketone. And you can go the opposite way, and we have NADH plus H plus goes to NAD plus, and it gets, excuse me, turned that way. So the coenzyme nicotinamide adenine dinucleotide, or NAD, its oxidized form is NAD plus, and its reduced form is NADH. So remember, if something is reduced, one way to tell if it's reduced if it has more hydrogens, and the NADH signifies that there is a hydrogen bonded to that NAD molecule. Therefore, it has two more electrons. This is a coenzyme that's synthesized in the cell from niacin, which is vitamin B3, and it is involved in reactions involving carbon-oxygen double bonds. So in the example of oxidation of ethanol to acetic acid, ethanol is the alcohol consumed in alcoholic beverages. It is toxic and must be metabolized and eliminated from the body. So in the body, it is metabolized to carbon dioxide and water in the liver. Ethanol is oxidized in several steps, and each step is catalyzed by an enzyme. So you can see we start at ethanol, and alcohol dehydrogenase is the enzyme that catalyzes the reaction, the oxidation reaction between ethanol and ethanal, or acetaldehyde. In a biochemical pathway, the convention is to show the structure of the main reactant or the substrate and the product on either side of a straight reaction arrow. This. While showing the abbreviations for the coenzymes on the reactant and product side of a curved arrow that intersects that straight reaction arrow. This convention allows us to focus on the functional groups that change on the substrate as it goes through a biochemical pathway, and also keep track of coenzymes involved in each step. So this first step, we start with NADH plus, goes to NADH plus H plus, and it turns into acetaldehyde. We are changing carbon oxygen bonds, so we're using NAD. Then we have acetaldehyde dehydrogenase is the enzyme that catalyzes the second oxidation reaction. So acetaldehyde goes to acetic acid. And then there are several steps in between with different enzymes catalyzing them. And the final products are carbon dioxide and water and energy. Enzymes are needed to catalyze the oxidation of ethanol to carbon dioxide. And this is what I just showed you on the other page, on the other slide. If enzymes cannot keep up with the intake of ethanol, then the buildup of acetaldehyde leads to nausea, headache, dizziness, etc. So if your body cannot keep up with, you're getting too much ethanol and it's being oxidized to acetaldehyde, but there's not enough time and you can't convert it to acetic acid and all the way to carbon dioxide and water, it starts building up in your body and it can lead to nausea, headache, and dizziness. So another coenzyme is flavin-adenine dinucleotide, or FAD, and FADH2. The oxidized form is FAD. The reduced form is FADH2. FADH2 has 2 more hydrogens than FAD, therefore it is the reduced form. This coenzyme is involved in reactions involving carbon-carbon bonds, or carbon-carbon double bonds. It is derived from riboflavin, which is vitamin B2. So for practice, the reaction shown is one of the 10 steps of glycolysis, the first biochemical pathway in the metabolism of glucose. Which functional group has changed in this reaction, and are the carboxylate functional groups affected in this reaction? So we look at what's different between succinate and fumarate, and we see that these are the carboxylate functional groups, and they haven't changed. What changed is this single carbon-carbon single bond to a carbon-carbon double bond, which makes sense because the coenzyme FAD is used for carbon-carbon double bonds. Is the substrate oxidized or reduced in this reaction? So we go from carbon-carbon single bond bonded to 4 hydrogens to a carbon-carbon double bond bonded to 2 hydrogens. It decreased in hydrogens, so lost hydrogens, and therefore lost electrons. Knowing oil rig as our abbreviation, oxidation is loss of electrons. Reduction is gain of electrons. So since it lost electrons, it was oxidized, and so it lost electrons. And you can tell because the hydrogens are gone. What is the coenzyme in this reaction? It's the FAD. Remember, coenzymes are on top of the curved arrows. Is FAD an oxidizing agent or a reducing agent? So because FAD goes to FADH2, so FAD goes to FADH2, it increases the number of hydrogens. It is reduced itself, and the substrate or whatever is reduced means it is an oxidizing agent. And also, since succinate was oxidized, the coenzyme is what helped make that oxidation happen, and therefore it is an oxidizing agent. FAD gained electrons, it gained hydrogen bonds, bonding to hydrogens, and therefore it underwent a reduction. For the oxidation reduction reaction shown below, determine whether the substrate and coenzymes have undergone oxidation or reduction. So go ahead and pause the video, and then when you're ready, come back and we'll do it together. So for this first one, we're looking at the substrate and coenzymes. Our substrate is acetaldehyde, and our product is acetic acid. We see that we go from an aldehyde to a carboxylic acid. We increase number of oxygens. We lose, so if you increase the number of oxygens, means it is oxidized. NAD plus goes to NADH. NAD increase the number of hydrogens, therefore it was reduced. If you increase your number of hydrogens, you're reduced. If If you increase your number of hydrogens or decrease your number of oxygens, it's reduced. If you increase your number of oxygens or decrease your number of hydrogens, it's oxidized. So I'll write that up here. Increase oxygen, decrease hydrogen, it's oxidized. Decrease oxygen, increase hydrogen, it's reduced. So in the second one, we see that we go from a single bond here to a double bond. So a single bond to a double bond, we write our hydrogens out. We would have a decrease in hydrogen, which means it's reduced. Sorry. Oxidized. FAD goes to FADH2. You increase your number of hydrogen, and therefore it is FAD is reduced. So in summary, coenzymes are required by some enzymes to carry out their function and are the oxidizing and reducing agents. Oxidoreductases are a class of enzymes that catalyze oxidation reduction reactions, and they require a coenzyme. NAD and NADH is a coenzyme involved in reactions involving carbon-oxygen double bonds. And FADH2 is a coenzyme involved in reactions involving carbon-carbon double bonds.